Hello everyone, welcome to the MIT Category Seminar. Today we have Bob Coecke from Oxford. He's going to talk about quantum natural language processing from his pub. Hi Bob.
Hello everybody. I know not everybody can say hello back, but I assume you're doing that to some extent. So you are in my pub, which is probably the only one which is still operational in the UK and in most of the world, to some extent, I assume. I've been working here the last few months because usually I spend my evenings here, but now, I spend my days here too. And now I also give my seminars here. So usually I work at the University of Oxford. This particular work was with a company called Cambridge Quantum Computing, and in particular with Alexis Toomey, Giovanni De Felice, and Konstantinos Mechanizidis. And so what we did is we did some quantum natural language processing. Now I'll explain what this is, and the idea is that with this company, Cambridge Quantum Computing, we're going to try to push this to actual practical technology. And so what I want to explain today is the science behind it, which is a bunch of category theory to some extent, and the kind of implementations we recently did starting from that. Okay, so I've tried to set up a workable seminar environment here. Let me turn the camera to the screen. I'll do that now, which is somewhat prepared. Oh, there you go. I think everybody can see this and read this. So, quantum natural language processing. That's what it is about. I mean, if you want to read about this after the talk, there is like a medium blog by CQC, which we wrote about this. There is a GitHub where you can see the experiments. Today, there was an archive paper on some tools which are actually much more general than this QNLP stuff. This is just a toolbox for model category stuff in Python. So you find this on the archive today. Like I said, all of that stuff was done with Konstantinos, Giovanni, and Alexis. There's a paper forthcoming also in addition with Stefano Goggioso and Nicolas Chipato. And I mean, since I'm a Twitter newbie, so since recent I post some of this stuff on Twitter where you can see this. Okay, what did we actually do? I wrote this down here. So we worked with a 20-qubit IBM quantum computer, and we told it some stuff, the computer, and then we asked it some stuff. And then the point was, of course, that the answer it gave on the basis that it was told made some sense. And the key thing, which I think, given how simple the setup was, if you compare to like question answering with AI, is that the quantum computer actually understood the grammar. Because otherwise, this wouldn't have made sense. It couldn't do this if it wouldn't have understood the grammar. So this is very different from a lot of standard and mainstream NLP already from the outset. And in particular, it composed meanings. It composed, okay, you see the word composing arising here, like in compositional and stuff like that. And that's really what it is. And that's what we are going to try to explain you today, that there is like a very tight connection between quantum and the way things compose and natural language and the way things compose there. That's the key thing. So the first thing I will try to explain you is quantum compositionality, which is an old story, then natural language compositionality, and then we're going to start bringing those two together. And that all will then end up on a 20-qubit quantum computer for now. So we've got access to the 53 one now, and there will be bigger and bigger and bigger and bigger coming. I'll talk about some other implementations besides the IBM one a bit later. So, but yeah, so it's really from very fundamental quantum stuff to the extent that we reformulated a long time ago quantum mechanics, fundamental stuff on natural language meaning, put that together, end up on a quantum computer. That's the story here. Okay, So I'll now start with the actual talk. I hope I didn't forget to say anything. And what I'm going to do, rather than wipe this off, because this blackboard has never been used before, so the backside is very clean. And I can just turn it around. Okay, I'll do this now. Go a bit out of the screen, because there's not enough space there. Here, turn it around. Up. Right, so I can write here. Ooh, there. Right, good. Okay, so I'm gonna write here. I take my chalk. You know, like this is also very unique to still be able to use chalk, because at the university all that stuff has been forbidden for a very long time. And at least I can now use chalk in my own place. Okay, so I'm gonna start very basic. So we're gonna reformulate quantum mechanics. This is a story which goes, if I'm in front of the blackboard, scream at me. If this is not readable, but because I can't really see it myself. So this story is about CQM. That's called categorical quantum mechanics. That goes back to 2003-ish. In 2004, there's probably the most recognized paper with Samson Abramsky on this subject. And the idea really was to redo quantum mechanics in an entirely compositional manner. At least that was my motivation. So because composition is such a basic operation, it would be really cool if you could reformulate quantum mechanics in that way. I mean, as far as structural reformulations of quantum mechanics came before that, composition was never considered. And even worse, composition is actually what killed all those approaches. So there is approaches going back to 35, like John von Neumann started it, and then he started to work with Gerrit Birkhoff on it, and they came up with something which was quantum logic, and they used like ordered structures to reformulate quantum mechanics. And a lot of people worked on that, like in the previous century. It was a big business, but it basically died because they couldn't contribute anything really new. And especially when quantum computing came, it was clear that whatever was produced there was pretty useless from that perspective. So one of our test cases, of course, living in this century now, is what we can contribute to quantum computing, and that has already happened. I mean, this talk is about something, of course, but there's some other things. So I'll say a bit more about that later. So CQM, I mean, basically this is about graphical representation. If you want to, it's categorical quantum mechanics, so you can do this all categorical symbolically, and then you actually make things unnecessarily complicated. That's a different talk. So I'm just going to do everything graphically today. So states in CQM, so the state, which is a concept you've got in computer science, you've got this in physics, we represent just by a simple triangle, like that, with a wire coming out. An effect, I'll say a bit more what is this later. That's the simple triangle with a wire coming in, and a general process by some sort of box with a wire coming in and a wire coming out. So this is just a process like in flowcharts. There's this special case of a state, which there's nothing coming in, something coming out. So it's a box, and the reason we represent it like that is if you rotate this a little bit. Okay, how should I do this? So yeah, so you take this one, you chop off this corner and this corner, and if you then rotate this thing, you get something like this. Oh, is that the one I want? No, I want the other one. Sorry, I want this one. You get like this, and then if you stick a psi in there, then this is like a state in quantum theory, like a cat, like a Dirac cat. So that's the reason we use triangles. So I ordered yesterday from Bezos 2 vinyl board wipers. No, 2 days ago, but he didn't deliver them yet. Bezos. Okay, sorry. Right. So okay, states, something goes out, nothing goes in. Effects, that's kind of the dual notion. It's a bit less standard, of course, in many theories, but you should think of this as some sort of test. Like, is this true? Is this true? So you test, for example, is the outcome of a quantum measurement this? And so this corresponds, of course, to the dual of this cat which I showed. So that's sort of a Dirac bra. Let me write this underneath here. So this one corresponds to, if you want Dirac notation, to a cat. This one corresponds to a bra. And then if you compose the two like this, then you get a bracket. Right? That's why we use this triangle notation, because it sort of mimics this Dirac thing. Anyway, so this is states, effects, and general stuff. Now, okay, I'm going to erase this because that's just very dumb stuff. You can apply to anything. So the key thing about categorical quantum mechanics is that you pick out some very special states, namely this one, and I'll explain what this means if you don't know this notation. And we will represent this one by cup-shaped wire. And then we take this effect and we represent this one by, oh, that's too close for comfort. Okay, that means this again. So this is cup-shaped wire, and this is the cap-shaped wire. So I mean, if you're not used to Dirac notation, this 0, 0, like this means just the tensor. So this is a thing. This is a thing which lives in C square tensor C square. So you take, say, you got a basis, and you take the first basis vector here, you take the second basis vector here, you tensor them, and then you take the first basis vector here, you take first basis vector there, you tensor them. Here you take the second basis vector here, you take the second basis vector there, you tensor them, and then you add them. So that's what this means in vector space notation. So you define these two things, and then I'm going to do a little proof here. That's the sort of stuff which you can easily do on a blackboard rather than slides. So what we're going to compute is, I mean, of course, many of you have seen this a million times, this sort of thing. If you read John Beiser's blogs for a long time and stuff like things like that. Little calculation. So we stick here this cap state. We stick this cap state here. We put this, cap effect. We put the cup state here. We put the cup state here. Here we put a piece of identity wire. There we put a piece of identity wire. And we want to figure out what that is. Now, how do we do that? So I'm going to now sort of use some hybrid notation, which is half Dirac notation and half graphical reasoning. So basically, if you remember how we defined this. This was a sum. Now I'm going to use sum notation like that of a basis vector of the first and a basis vector of the second. So this would be something like I, where we're running through different basis vectors. So we went through the case 0, 0 and 1, 1, and that's all. But to do this calculation, it's easier to work with this sum notation. So what we're going to do is, our basis vectors are, of course, states. So we can stick a state here, I. We can stick a state there, I. And then we sum them. Funny thing is, I can put my sum wherever. I can put my sum in the middle. It doesn't matter where I put my sum, because the I points at these two. Okay, we replace these two as well. J, put my sum somewhere, wherever I want. Sum. Oh yeah, you see, ij, so that creates a delta ij. So all the i's and j's are the same. So what we get is really the sum over I of this. We don't need this anymore. And that's the resolution of the identity. So we get the identity. So bottom line, what we just computed is, I'll leave this up. Okay, this is on video, so you can rewind if you want to. The bottom line is what we just proved is that with the notations we used, you can, what's this, the geometry? Compute this, and you get that this is equal to the identity. So basically, if you got something which looks like a wire, it behaves like a wire, you can yank it. And in category theory lingo, this means we're dealing with a compact closed category. Basically, this means if you take all linear maps between Hilbert spaces, well, let's say vector spaces for now first, vector spaces first, you take all, well, no, say Hilbert space, because this happens to be the adjoint of this. So we've got adjoint involved. Hilbert space, you take whole linear maps between Hilbert spaces, and you add these two bits to the structure, these cups and these caps, then you get a compact closed category. You get a compact closed category. This goes back to Kelly a long time ago. So you get a compact closed category. And you can, and this means you can do some topological reasoning about quantum protocols. You can do some topological reasoning about quantum protocols. Let's do that. And that was a little bit the initial claim to fame of this categorical quantum mechanics. So this goes back very long now. So you got Alice, you got Bob. Now, Alice and Bob share a very special quantum state, which is called the Bell state, and which was actually this cup thing I was talking about. Alice has a state psi. She wants to get to Bob over a long distance. So how does she do that? She applies the cap thing. And here is an identity. So the thing about these diagrams is what really matters is how things are connected, and of course the endpoints you have to care about. So whether this state is here and then there is a piece of wire, they're all going all the way to Bob, or we would just write it here, it's the same. It's an equation. It's the same. So basically it says is if this protocol is done, like Alice has this state, they share this Bell state, so one particle here, one particle there in this special state. Alice applies that cap there, then boom, that thing ends up there. Now I'm not going to go into some caveat on this one. The caveat is that quantum mechanics doesn't really like you to apply these things. I mean, it makes it part of a lottery. It makes it part of a lottery. Like, if you want to do these things, sometimes you can, sometimes you don't. Now, the reality is that the experimental physicists in the lab and the best in the world, like in Vienna and all that, who were the first one who did this stuff like that, even now they say, okay, let's just hope we're lucky. And this is called post-selection, and then they do that stuff. But there's other ways to deal with that. The reality is that you actually have to send a message from here to there, that whenever something else happens here, that you sort of adjust a bit for it. That's not important. The important here is the geometry of this picture. The geometry of this picture, which underlies this principle of teleportation, is that by doing something here, you can get this to move there, if you do the right thing. Okay, check out this picture. So you got this, which is a resource state. You got some other state, and then this cap is used to make this interact with this one and end up there. I mean, I can change this picture a little bit and do something totally different, which you will never find in a physics book. I mean, there's no reason you wouldn't find it, but so I'm also going to get rid of Alice and Bob. Okay, here. So something you could do too is you've got, let's call this Alice state. Let's call this Bob state. And then here we got like a crazy state on three systems. I mean, there are lots of crazy states on three systems, like this is a story in itself. And then we can actually feed Bob and Alice in this crazy state, which we call the interaction state, I, and then something comes out. That's something you could do physically. So you make this, you take the state A, you take the state B, you make them interact by this big three systems quantum state here, and it spits out something. It spits out something. So that's something you could do in a lab. Now, I mean, people have done this with special states like GHZ states, and they have done things like that. But the reason I put on this picture now, you don't know, but you'll realize soon after, when I stop talking about categorical quantum mechanics, and I start talking about this go, and then between brackets cat. Because, I mean, Discocat. The reason I put the cat between brackets is Alexis and Giovanni want me to kill the cat. I mean, if you want to know why, well, basically, so Discocat means distributional, compositional, and this means categorical. And they say this is completely redundant to have compositional and categorical. But actually, they say something much more flattering to me, like this go emerged in the context of natural language and how to compose meanings in natural language. So I'll say a bit more about that later, but so in language theory, you got things like grammar, but you also got things like meaning. I mean, people didn't really consider them that much in the sort of mathematical end. They were basically talking about grammar and stuff like that. But I mean, there's of course meanings to words, however you want to formulate them. Just think about it abstractly. You got some meaning, blah. And then you want to compose meanings, because a thing which we know how to do is to, if we know all the meanings of a word in a sentence, and a sentence is grammatical, we know the meaning of the sentence. We don't need to look a sentence we never heard before up in a sentence dictionary, except if it's some really weird thing. But typically we understand the sentences which are made up of words we understand. So what Discocat at the time did was provide an algorithm to do so, where these meanings could live anywhere in any space, and these spaces just have to be able, you have to be able to organize the spaces in a certain thing, which is a compact closed category. And now, due to some result by Antonin Delpertz, this is no restriction whatsoever, because you can always stick them one way or another in a compact closed category. Initially, the people in linguistics and natural language, they were like sticking things together they took words, they were just adding them, they were multiplying them, random stuff, and then they sort of, what works best? I mean, it all worked extremely bad, because it didn't even take account of the order of words and stuff like that. It was a complete mess. And so then we actually came with an algorithm which really took into account the grammar and all that, and of course produced very good results. But now these kids say, Alexis and Giovanni, yeah, there is really nothing else around, so you don't need a special name for it. Just call it distributional composition. Okay, so we kill the cat. So this goes back to about 2008 now, with Marnouch Chandrazadeh and Stephen Clark. Marnouch is now at UCL, and Steve is at Google DeepMind. So what did we do? It was funny. I met with Steve in the, I met with Steve, I forgot to do something, I'll do this later. I met with Steve in the print room, who was in my department then, and said, hey Bob, I hear you're a physicist, explain me what a tensor product is. I said, okay, what do you want to know? Yeah, in natural language, like there's this problem in natural language processing that we don't really know how to compose meanings of words to produce some phrase or a sentence. So we need a way to do that. I said, okay, let's think about it. So that's when we start working on that, and we got somewhere. So here is what we did. So I'm going to start with something which is called, I'm going to write the name, Lambeck. I mean, this is category theory seminar, so Lambeck is a name obviously everybody here knows. But Lambeck, 1999, may sound a bit weird. So Lambeck started all this maths of grammar business in the 50s, and became famous with that. So in 1999, he kind of changed his mind. I'm going to explain the sort of gadgets he started to use. So I'm going to write here an N. This N stands for noun. This is noun time. And I write another N here. This N stands for N, noun time. So we're thinking about a sentence now with a subject, transitive verb, and an object. Like Alice hates Bob. Alice hates Bob. So you got a noun, Alice, a noun, Bob. Now, hates. Hates is transitive verb. So it turns out in these grammatical gadgets that transitive verb is not a primitive thing. So you can't just write down a simple transitive verb. It's made up of other stuff. Like it's actually a composite thing. So what is it made up of? A sentence, I mean, this may be weird, a sentence and a noun on the right, but something like the inverse, right inverse of a noun on the left, right inverse. So this inverse actually means it's missing a noun on the left, it's missing a noun on the right. And that's why I have to stick in a subject and an object to actually produce a sentence. So once you do this, noun, transitive verb of this shape, now, then you can, these two cancel out because you got a noun and an inverse on that side. You got a noun and an inverse on that side. So these cancel out. And what remains is a sentence. So this reduces to a sentence as a whole. And that's how these gadgets work, these grammatical gadgets. This goes back to Chomsky and all that in the 50s. So these are these gadgets to figure out whether grammar is correct. Now, what I did was scratch. There is actually a different way to do this or to represent this calculation, a little bit more like in particle physics annihilation. We can say, oh, this one and this one, they annihilate each other. They come together, so whoop, time goes up, they come together, annihilate each other. This and this one, they annihilate each other. This one goes through, and I mean, you see this cap showing up here. Okay, so that's Lambek, and he called these pre-groups. These aren't really groups because there are these inverses which are not supposed to be the same. And basically there's also a partial order. So there aren't really equations, there are inequalities, because if you would do this with equations, you get a group anyway. But by going down from equations to inequalities, you can actually make sense of something like that with a left and a right inverse. Right, okay. I mean, all these grammatical things for categorically, this category theory seminar. So the old Lambek stuff from 56, they're actually monoidal closed categories, non-symmetric. So you got left and right adjoints. Then later, Lambek in the 80s came up with something Christian Lambek, and these were actually star autonomous categories. These Lambek pre-groups are compact closed categories. So we got compact closed categories. Okay, so this was already when Steve Clark told to us about, yeah, we don't know how to combine meanings and grammar and compose things. We were thinking, oh, wait, like these people in NLP, they use vector spaces and stuff like that to represent their meanings. Vector spaces make up a compact closed categories, so they're pre-groups. So, oh, we should do something there. And basically all we needed to do was not to think of these as grammatical types, but to think of these as spaces in which meanings live. And so we stick a meaning here, say Bob, a meaning there. For example, Alice's state, a meaning here of a verb. Call this I of the way they interact. This could be like Alice hates Bob. And suddenly I got a diagram. Let me use another color to make it actually clearer. Suddenly I got a diagram where Alice is feeding, I'm going to put an arrow here. Alice is feeding into this verb. Bob is feeding into this verb. And then this interacts like Alice. And then it spits out the meaning of a sentence. It spits out the meaning of a sentence. So that's how simple it is. You replace the grammatical types with the spaces in which meanings live. And then, I mean, it makes perfect sense. Like, so the word hates doesn't mean anything. It's waiting for a subject and an object. Who hates who? Alice hates Bob. And then this diagram makes hates flow. So literally, Alice is teleported, if you want, teleported inside there. Bob is teleported inside there, and then spit out the meaning of that thing. Okay, so that was Discocat. What do I want to say? Like I mean, the thing is, like in practical NLP, people use vector spaces, as I think most of you may know, like to represent these meanings. So this is exactly the same picture as I wrote down before. And I mean, at that time I was talking about Hilbert spaces. There is an inner product. What does an inner product mean in these contexts? Well, an inner product allows you, so basically what comes out here is the meaning of the sentence Alice hates Bob, if you want to. So what the inner product allows you is to see how similar different meanings are. So how close is Alice hates Bob to Alice doesn't really like Bob, for example. How different is it from Alice loves Bob, for example. So you can actually start computing these inner products and then see how these different meanings of sentences compare. People were already doing this for like computing word similarity, but they didn't have this mechanism to go from words to sentences like this one, which I proposed here. The word you could call this is semantic distance. Okay, so so that's maybe what time is it now? Okay, are there any questions? Questions? Everybody's asleep?
So there have been some technical questions in the chat, but Alexis has answered them actually very well.
Oh, Alexis is there. Ah, hello, Alexis.
Hello.
Cheers.
Cheers. I think someone is asking, are the inputs, outputs of Word labeled to know which ones are allowed to match? And I think because you drew the wires so thick, you've erased the basic types that are the labels. Yeah.
So yes, that's of course a good point. So this is sentence type. This is sentence, but I didn't want to say too much about this because people are going to ask me, so what is a sentence type? And I don't want to give a simple answer now because I'm going to give a much better answer later within the context that we're actually using. So this is noun. This is where nouns live, whatever this is. This is where sentences live. I mean, noun, this is again noun type. The transitive verb is a composite of noun, sentence, so it's a tensor product. So this lives in N, tensor, S, tensor, N. So this is a big space. This is a big space. And I mean, I'm immediately gonna go into that. Why this is maybe not that good. Okay, I've taken over the drink. So one thing I forgot to say, I mean, I have to do this, is about the quantum stuff and also the mathematical background to all these diagrams and all that. This is the place where you read about all of that. So this is a book about the quantum, but I mean, all these diagrams from language, we actually talk about the language stuff in our side. You find all of this here. So, and you don't even have to know category theory to read this. You don't have to know quantum mechanics. It's big, but we teach, Alex Kissinger and I, we teach this in 20 hours or something. So I mean, yeah, whatever. It's thick because it has a lot of pictures. But this is the thing you want to read to learn all this sort of stuff. Yeah, okay. And for each one we each get a duvel beer. That's kind of the deal we have with the publisher. Okay. Any more questions? I guess not. So let's go on now to QNLP. So I think this goes back to the idea, 2015 or 16, and that was with Will Zhang. Was then doing a PhD with me, and then went to work for Rigetti, where he did some stuff, and now we're sort of starting to work again together because he moved to other places I'm not going to name. And it's really the idea I was just telling you about, like these diagrams of the language are the same as the diagrams of the quantum. In fact, like they're both even dealing with vector spaces and all that. So why don't stick language on quantum systems, or why don't stick language on a quantum computer? I mean, there was a little bit more to it than just that, but I'm not going to go too much into it because I'm going to give our new version a bit later. But like one of the big upshots of that, that was the first reason I thought about this is exactly if you got something like a verb, like this is a tensor of a noun space, a sentence space. That's huge. That's huge. If you take noun to be a million and say you're generous and you take sentence to be the same as noun, then it's a million times a million times a million dimensional. Too big. I mean, this is a very naive approach to do it like that. I mean, if you think a bit about it, you know that this already reduces to noun times noun for reason I'll explain later. But still, it's big. Now, if you do this on a quantum computer, it doesn't matter. It doesn't matter. It's just like 1, 2, 3 systems. It's just like you don't have this tensor product comes for free. Then another thing which was actually worth considering was that we had been using density matrices in the context of Discocat. So density matrix is what you use in quantum mechanics if you don't know exactly which state you're dealing with. It's sort of probability theory over quantum states. And we had used them to deal with linguistic ambiguity, which is very important. This was work by Dimitri Kartsaklis and also Robin Pied-Deleu, who may be known to this community. And then also with Marta Lewis and then Marsden, we had been using them to talk about entailments and stuff like that. Because if you take meanings in a vector space, like most NLP people do, then you can't really say that a tiger is an example of a big cat, and a big cat is a mammal, and a mammal is an animal, and so on. And with density matrix, we could do that because density matrices you can order in a very natural way. Well, not natural, well, whatever. Now, even more so, there is a bunch of quantum algorithms available which you can actually directly use. For example, if you want to sort of take the meaning of a sentence and you want to find which other sentence is the closest to it, there are quantum algorithms typically under the umbrella of quantum machine learning that are available there to do this like with a substantial speed up. So you have a lot of benefits to do it then. But I mean, at that time, I mean, there weren't any serious quantum computers really available that you could do anything on that would even make sense. They were a bit too small at the time. So that changed actually a bit. Now there were a few bugs. I mean, bugs is an overstatement. In this proposal, it wasn't our fault, but we were relying on something like QRAM, which basically means that you can pretty straightforwardly encode your data on a quantum computer, your classical linguistic data, which you can't. It turns out that it's not easy to do that. And also, we didn't fill in the details and the blanks because, again, it seemed at that time to be a little bit far away. But I mean, things have changed meanwhile. So, did I say everything here? Yeah. So, recently, then with Alexis and Giovanni and Konstantinos, we actually went on the machines and effectively did use this coincidence of quantum and linguistic, and we filled in some of the blanks, and there was some more work needed and stuff. And to actually, let me check the time. Oh, I'm doing okay. And so one thing we kind of need in what I'm going to explain is, which people in this community may also have heard about, is called the X. I'm not going to say much about it. Calculus. This goes back to 2008, where Ross Duncan and me, we were traveling through the mountains of Iran. And now like lots of people are doing similar things. This become a very... So this is about the interaction of different Frobenius algebra. So there's now a big topic like Brandon and Byers have done things with that in control theory. So that's closely related to this. And then Sobocinski and Zanassi and they have a whole bunch of Italians around them. They're all doing that. Robin Pied-Deleu is involved in that too now. So what is the ExCalculus from our perspective? okay, I need another color here. I mean, we use the green and red, which is a very bad choice, but this is just because that's the two pens I had in my office at the time, and it sort of stuck for some reason. So the ExCalculus, I mean, is basically got, okay, let me, instead of wires, you got something which I now like to call multi-wires. Like a wire has two ends, a multi-wire has multiple ends. And we denote this by a dot with all these multiple ends coming out. And in the context of quantum mechanics, they actually correspond to different bases, orthonormal bases. So say this one corresponds with the 0,1 basis, and this, so like which you could write like this, 0,1. Okay, I should have used green, of course. And the other one would really correspond to the other bases. They typically call them plus, minus, or something. So basically what you do is, in the same way that, like you remember the cup was just sum of basis vectors, you do this the same now, but like now you got a bunch of inputs and outputs, and then it turns out you get something that typically depends on the basis. Moreover, it defines the basis. So these things really correspond to the two bases. Now, there's a whole bunch of rules you can come up with them, and recently, people like Kwang Wang and some others, they actually came up with rules so that any equation you can establish with linear algebra and Hilbert spaces, you can actually do with these things and some graphical manipulations. So now this, I think this is a really big deal, independent whether you're interested in quantum mechanics or anything like that. The fact that for a theory like quantum theory, you can come up with a graphical calculus which produces all equations for you. That's a big deal. I mean, you can't deny that that's just an incredibly big deal for graphical reasoning. I mean, I wouldn't have believed that it would be possible. We knew we could get fairly close, but really getting there, that's just crazy. Anyway, so we're there now. I mean, it still can be improved. It's a matter of like making these rules nicer. But anyway, for now, the talk of today, there are these two things which correspond to base. And the only rule you have to remember now, I mean, and this is a rule which really represents the idea that they are multi-wires, is that if you compose some of these things, so there can be lots of legs here, lots of legs there, lots of legs there, then they fuse together in a single one. That's all you need to know. All you need to know. So, I mean, I didn't even have to tell you because I call them multi-wires. What is a multi-wire? A multi-wire is something that has multiple ends. What do you do with a wire? A normal wire with two ends? Well, if you take two wires and you connect the ends, then you get one long wire. Same thing, if you take two multi-wires, you connect them, you get one big multi-wire. I mean, that's the same thing. Same principle of a wire. So, and this rule is kind of explaining that. That's all you need to know for today. Well, is there anything else? Okay, so now these things are pretty useful if you talk about stuff like quantum circuits and even classical circuits. It's the same story. That's some idea which Yves Lafont actually realized a long time ago. And that's that if I, for example, plug these two together, like a green one, the 0,1 basis, and a red one, then this is C0 gate. This is C0 gate. This is C0 gate. So you can reproduce, and then basically what this is like the usual rules of the ExCalculus, which are more than, so the fusion stuff means green fused together and red fused together. It doesn't say anything about the interaction. For what I'm going to do today, the interaction doesn't really matter that much. It's really about like just this fusing stuff. It's all I'm going to need. But if you take all these other rules, then you can actually come up with rules to simplify quantum circuits, for example, or classical circuits. And another like recent thing which people who have involved in that is Alex Kissinger and John van der Wettering, Kwang Wang, again, Harvey Wang, and Neil de Potrap, and Ross Duncan, and some more people, is to actually come up with tricks to simplify quantum circuits using this ExCalculus, because quantum computings are pretty poor at the moment. So if you do one of these gates, it's really expensive, and you can only do a few of them. So if you can simplify the circuit you try to implement, even with one gate, it's a big deal. It's a big deal. And the state of the art now for a while for things like, I mean, I'm not going to go into the specification of what it is set by using these ZX rules. So there is stuff like PyZX around, software that does it for you. And at CQC, they have a compiler, which is the one we use to stick stuff on a quantum computer. And the optimization is done by ZX because it's better than the rest. It's the best thing, which is that. So from the ExCalculus, you now got the best quantum circuit optimization. I mean, it's sort of nice that it's all part of the same family, because this is part of the family of categorical quantum mechanics. This was categorical quantum mechanics being more expressive than just using cups and caps. Okay, so did I want to say anything more about this? Are there any more questions? No. I mean, just like other equations, for example, is that these things form a bialgebra, even form a Hopf algebra with trivial antipode and some more stuff. So there's a bunch of which are exactly the same as you find in many of the papers of John Byers and Brendan Fong and Pavel Sobosinski and Zanassi and all these people. So it's similar rules. Okay. I don't think I'm going to write on the blackboard anymore. No. So now I'm going to really go to the hardware implementation of quantum natural language processing. I can just leave this here. So I'm a pretty handy person. So I screwed some things in last night to help me save some time. So I've got a bunch of these like pieces of paper here. And okay, so now I'm going to talk about quantum natural language processing. So I'm really thinking of all this stuff now sticking on actual hardware. And the first I'm going to talk about is optics, optical hardware. So just before Corona, Giovanni went to Vienna, where there's Philip Walter, which used to be before the Zeilinger group, which were the people who first did quantum teleportation and quantum optics. And so they were going to implement all this QNLP stuff on this quantum optics stuff, and then they all had to go home. So I hope, I mean, if they open up Vienna again, we're actually going to do this. So this is the picture this is the picture you saw before to some extent. So this is the Alice Hates Bob type thing. This is the Alice Hates Bob type thing, but we do something more here. So I think if you remember well, Alice Hates Bob was something like this, a sentence. I'll put a type now, sentence. Noun. Okay, noun. Alice, Bob, how they interact, hate. So this is actually an example of that. Now I did something more here. I mentioned before. So now all these wires here are noun. They're all noun because one does the clever observation, and I don't have too much time to go into that. That is big I thing. I mean, it makes a lot of sense to think about this as first take the sentence space to take. So this is the sentence space. Take two noun space. These are the two other noun spaces, and then you take one of these dots from the ZX calculus, and then now something with two wires. And basically what this does, you have to think of this as a proposition. This is a proposition which takes Alice and Bob, and which a bit like a gate, like which sort of, or an entangling gate or whatever you call it, which expresses the fact that now Alice hates Bob. I mean, this could be Alice marries Bob. I mean, if you want to be nice. So this would be sort of thing which establishes that now they're married. So that's what I did here. So I substituted this one with this one, and then you get something much simpler, like this. Okay. So let's go to a slightly more sophisticated sentence, which has a bit more of these dots inside. This one. I mean, it's again optics. This is stuff. So here's the thing. I should say that. So with quantum optics, you can directly implement this stuff. You don't have to change the form or do some compilation. You just stick this on an optical table. So these are states which you prepare on your optical table, and this is some sort of operation which you then call fusion. I mean, this is something people have been doing a lot. For those people who've ever heard about measurement-based quantum computing, for example, how you do things like that. So this is what you directly do on an optical table. Here is a slightly more sophisticated sentence, which is a lot cooler, which you can also do on an optical table. And this is, okay, this is with relative pronoun. This is with relative pronoun. She who hates Bob. So this is a typical example. You should actually, she who hates Bob, if your model of meaning and all that is good, I mean, you should be able to figure out that this is actually Alice. You know, if you got enough context, you should be able to figure out that this sentence as a whole, well, it's a noun phrase, so this is noun type because it's a noun phrase. This is noun, everything is noun now, everything is noun. I mean, I kind of delete the sentence type here. I'm not going to go into that, but I kind of deleted the sentence type. And this is what actually who does. It would have a delete operation here, which goes into the sentence and then deletes the sentence type. That's kind of how it works. But who can be nicely represented by these dots from the ExCalculus. I mean, it basically means you take an orthogonal base or something with it. One can discuss a long time about it, but for now, take this for granted. Which is also nice. What it also shows is that words like who and some other words can actually be given structural meaning. So these are things which live in your categories, structures. This goes beyond the grammar, that actually you end up giving meanings by using pieces of your structure. Like here, technically this is a dagger, what is it again? Dagger special commutative Frobenius algebra. That's what it is. It's dagger special commutative Frobenius algebra. So for a quantum optician or for any quantum person, this is G at Z state. It's called a G at Z state. People in Vienna are incredibly good in making them. Again, they were the first one to ever make them. So they're incredibly good in making them. So the people in Vienna can actually do this state, they prepare this state, they prepare their G at Z state, they prepare this, they prepare this. They can of course do these ones too, because they were the first one to do teleportation. That's where they use this stuff. So they can do all of that. And it's really crazy. Like this is sort of the preparation, which is the meanings, and then this are the measurements. So you got preparation is meaning, measurement is grammar, and what comes out is the meaning of the sentence. So that's what the people in Vienna can do. So that's the optic stuff. So like I said, like this would probably already have happened even if it wasn't for Corona. Now, when you work with this IBM computers and stuff, then you can't leave things like that because they work with circuits. You have to give things as a circuit. You have to translate everything to a circuit. And we used the thing which Alexis and Giovanni put on the archive today, which is Discocat, which, like I said before, is for dealing with monoidal category stuff and functors, like monoidal categories and functors, very general library and all that. So that's how we did this automatically. The conceptual way how you would do that is you look at this picture and say, okay, we have to turn this into a circuit one way or another. What sort of, not just any circuit, a circuit where you can use stuff that a quantum computer knows how to use. So in the first approximation, I mean, this doesn't look like a circuit. This doesn't look like, I mean, a circuit, I mean like what classical is the reversible circuits, where you use things like C-knots and reversible gates. So in this quantum case, it's like unitaries and stuff like, okay. So basically what you can, you know, this and this, they fuse together. They fuse together. So instead of multi-wire here, with 3 wires, and a multi-wire with 1 wire, which is less than a wire, of course, but it's still a multi-wire. So these ones would fuse together. So you basically get A is connected to some output, and A is connected to this I. Now, of course, this I looks like a box now instead of this. But I mean, this is a standard thing, like with compact closed categories, and it doesn't matter whether the thing is an input and an output. So a thing with 2 outputs, I can turn into a thing with an input and an output easily. So this this output actually becomes an input. So I got A going in an input here, and then there is the side track with this green dot taking something out, and I do the same there. I do the same there from the output of I. I do the same there, and so that could be. So I actually translated this thing into a circuit, and this is the sort of thing you can actually stick on a quantum computer. Now you're not done yet, because this I thing, quantum computer tells you, hey, this needs to be unitary. So this needs to be, if you compose it with set joint, if you compose the pictures with flip picture, that's what it really means in picture land, then you need to get the identity, and the other way around too. Okay, so that's another restriction. You can get around that by introducing another particle and then tracing part, but I mean, it becomes expensive. So there are, I mean, maybe you can use singular value decomposition and stuff like that. Like there's ways to deal with these two to make it as circuit-like as possible. I mean, this probably you wouldn't encode as a state, but you would encode as some sort of box itself, which you then encode on a fixed state. But anyway, it's circuit shape, so that's good. That's good. We can try to do the same for the other sentence. I mean, it's kind of funny because optically it's more complicated. Optically, it's more complicated. Circuit-wise, it's kind of simpler. It's simpler. Yay! Okay, you got this. It's because the green dot is already there. You know, you got the state G goes into the green dot. If I didn't do it wrong, yeah, so B goes into I. So this is actually a different I than on the previous picture. This is the I, the transpose. This is transpose. As a matrix, this is transpose of the previous I. So actually, I really should have put the transpose there if you compare it to the previous one. So it's a simple circuit. These are the sort of circuits we used and we put on the quantum computer. So what did we really do? Are there any questions now? Actually, I'm done pretty much. Yeah, I'm done in time too. So I'm done in time too. If there are any, I mean, the last thing I just wanted to say is what exactly we did. So I'll leave one of these circuits on. I take this one out and I'll write on that side of the board. Oh, don't fall, don't fall. Yeah, I mean, like half an hour before the talk, I was actually with a grinder because the screws were too long, grinding the back of the screws away so that it wouldn't hurt anybody. Because I just screwed them in to any of these things, realizing that would help me in time if I prepared some of these. Okay, so what did we do? What did we really do for the last 2 minutes? After I take a sip of my beer, if there's anything left, my beers, because I'm actually drinking these skeleton guys' beers too. They don't drink much. Right? Okay. So what did we do? I mean, you have to realize we're really working on a quantum computer with not that many qubits, and we actually, I don't know how many did we use, Alexis? Okay, you'll say later.
I think we used 5.
5. Okay, 5. So the reason
20 and 5. They had two.
Did you use 22?
We used the 20 qubit one, and then we also used the 5 qubit one.
No, I mean, how many qubits did we use on the 21?
Not so many. 5, I think.
Yeah. Okay. So 5. So 5. Okay. Right. So we started with a bunch of nouns, like a set of nouns. Doesn't matter how big it is, and then some verbs, some transitive verbs. Right.
Alexis, could you mute yourself? Otherwise, we see you instead of the board. Thank you.
Well, he's prettier than me. Okay, so then we actually, from these, we produced all sentences we could come up with. So which means we are using this compositional stuff I've been talking about, all this grammatical structure stuff, we just use that. We throw in all this stuff, relative pronouns, whatever. I mean, there were sentences like, Alice, who is rich, loves Bob, who is poor, and stuff like that, like combinations of the whole thing. Like, so you produce a bunch of sentences. Then we actually said, okay, now we have to declare some reality. So we weren't working with empirical data because it's completely impossible on what we had available. I'm going to take another color. So the next thing we did was, okay, we build the world. We build the world, if you want, out of these sentences. And this is, we declared which ones were true and which ones were false. So you get a bunch of sentences. Some are declared true, some are declared false. And it turns out in the way you set things up, this will somehow be consistent. I mean, the way we set things up, this will somehow be consistent. Then the last thing we did, and this consistency is very important because these different sentences interact with each other meaning-wise. They're not like totally independent statements. They interact a lot because obviously you've got a complex sentence with blah, blah, who is blah, blah, relative pronouns going on and all that, and other kinds of relationships going on between these things. Then there's a lot of interaction and meaning going on. Then we sort of did a cutoff and we say, okay, we're going to teach a quantum computer these, and let's ask it what it can figure out about the other ones. They're not independent in terms of meaning because the whole thing is kind of consistent. So we teach them these, we ask them those. So that's what we did. That's really what we did. I mean, we haven't written a paper specifically about the experiment because we want to make the experiment bigger and more sophisticated. Let me tell you something about. So what we did. So IBM got superconducting qubits. Superconducting qubits are kind of good to sort of use a lot of qubits. But they're very, you can't do much with it. Like if you hear about the quantum supremacy experiment, what they did very cleverly is actually use the noisiness of the computer itself to do something useful. Another thing they used is that the space you get if you have something like 53 qubits is humongous. That's exactly what we're using here to some extent too. We're using the extent that if you start tensoring these things, you get like huge meaning spaces. So you're working with humongous things. So one of the things we're shooting for in the near term is actually do a supremacy type of experiment or statement, which is a little bit more meaningful than whatever the Google guys did with their with whatever they did, which was just a show of force without actually any meaning to it. This is all about meaning, so it's by that reason alone a bit more meaningful. So, but yeah, so a lot of the things we're using is actually the space, the tensor space you get when dealing with this sort of grammatical structures. What else did I want to say? So yeah, we're actually trying to scale this up now using some bigger computers because actually our first experiments came out a lot better than we thought because Ross Duncan had been telling us, oh, these computers are shit. They do nothing. And they actually did a lot better than what he was telling us. Anyway, so, but I mean, I should at the same time say this, like all the compilation, which I was talking about, this ZX-based stuff, is stuff which was built by Ross and his team at Cambridge Quantum Computing, which is the ticket compiler. That's what we use to actually get things more efficient. So we're scaling things up. I don't know whether there's anything more I want to say before I close. Okay, so the key thing, like the key bottom line is we started with something very foundational, like changing quantum mechanics from the Hilbert space formulation is something more complete, more compositional, which we now know is to be complete for equational reasoning. So all this diagrammatic stuff, what you see here, for example. We did something similar for natural language. We started to think about how to compose meanings in a useful way. They turned out to generate the same compositional structures. We put these two compositional structures together. This tells us how to put language on a quantum computer using some more diagrammatic deformations, like using sort of the Swiss Army knife of category of quantum mechanics, this is the ExCalculus to do this. We actually stuck it on a quantum computer and yeah, we got something out. Like we were able to tell the quantum computer some stuff and then we asked it stuff and it answered pretty faithfully. It's a first experiment. We're pushing things further, see where we can get with this. And that's it. Let me check out. Oh, yeah, 5 minutes over time. Sorry. Okay, that's it. Yeah.
Thank you very much, Bob. So we have some questions. So Alexis and Konstantinos have actually answered some of them already. So people, could you please tell me which ones you have not answered or which ones you would like to forward to Bob? Feel free to speak.
This. I mean, I just want to say this is amazingly cool. Like I got these guys that are answering questions on the sidelines. It's amazingly cool, and I would give them a, you know, yeah. For the record, I did put, but like just before Corona took this is a music studio actually, and we do concerts here. Like Alexis was playing bass here, and usually Konstantinos is the local bass player. So instead of playing bass here and stuff like that, they're now answering science questions somewhere else. That's cool.
So are there any unanswered questions?
So there's one that just showed up is how many qubits before it's from a proof of concept to a real NLP system? Or how many qubits do we plan on throwing at this stuff?
I mean, you can help me answer that, Alexis, but I mean, I think we could do a supremacy thing with what's available. That's my guess. If you play it right, we can show that we can do something which you wouldn't be able to do on a classical computer already pretty much now. Now, how useful this is in the space of current NLP, that's a completely different question. Now, what I think, my belief is that this is going to make us do different styles of NLP than what people are doing now. Like this, for example, dictates a completely different way to think about meaning, which is, of course, much more compositional. What we did, which is not standard already here, is when we were teaching the words to the quantum circuit or doing the meaning, which was by you use this as a parameter. You use these things as parameters, and then you train the thing with your data. When we train them, they're already in a compositional context. They are already in a compositional context. So where standard, there was this idea of meaning, where people did things like to encode meaning. They looked at text, they did some sort of co-occurrence stuff. Here, it's really general compositional context, which is already part of the learning. So it's completely different learning paradigm from the start than most people are using. On the other hand, you can correct me, Alex, my feeling is that complexity arguments with these variational circuits aren't very clear yet. You don't really know how things scale, so that's something we need to learn, and it could be that it scales much easier than if you're just thinking in terms of basis, vectors, and size. Do you understand what I'm saying?
Yeah, that's thanks to the Bob. Yeah, that is my question actually. Yeah.
Okay.
Yeah, thanks. Yeah, do you have any sort of plan to interpret on that sort of your semantic meaning of that you are categorizing?
I mean, yes. I mean, yes. We need to come up with a different paradigm for meaning.
Yeah.
It's totally different. It's totally different.
I totally agree with that, such kind of point. Yeah, that's why in that I would like to know that it is already to interpret on the different version. In that several questions from this audience is what to back or some another sort of natural language tool. Can you already compare or not? Yeah, that's the one.
I mean, always,
such kind of planning. Yeah,
I agree. Like so what the natural language stuff mostly, which we did focused on this composition. We never really focused on what the meanings are. Like we abstracted away the objects, like if you want to say. But it's clear that the meanings themselves are not sort of living in separate spaces. That's a stupid thing. We've got some. If you go to some paper which we have, which is interacting conceptual spaces, then even there you got already sort of a compositional fine structure. You could say what a banana is by all the things it relates to in some way, but then a banana is not a static thing. Like you can have like an unripe banana, and the color of the unripe banana is green, and the taste is bitter, and then you got the sort of normal banana, which is yellow, and the taste is whatever it is, and then you go to the overripe banana, which is becoming black, and of course becoming more liquid and mushy. And you would want to have the meaning of banana be represented like that, which is a big tensor, like the unripe, like which is the first thing is about color, maybe the second thing about taste, the third thing about texture, and then you get an entangled state across these three different concept spaces, one about color, one about taste, and that's sort of a much more natural way how you would set up meanings here than saying some humongous vector space as people used to do in the back of words. Now with machine learning, it's not that clear anymore what the spaces really are, but this dictates you compositional space. You sort of compose your concepts from the parts up, and I mean, I think that's what it kind of dictates, but this needs a lot of work to see what is like conceptually sound and how it interacts with the way you're using it, because ultimately this is all about meaning in use. But it gives a completely different paradigm to it. It's not the sort of initial incarnation NLP has given to it. I mean, this is not even about language, you know, like meaning is such a big concept, like I mean, it's such a big thing, like it's pretty much about everything. So this is like compositional foundation for everything. I mean, I've got this crazy paper about like for quantum foundations to theory of everything, but I wasn't even thinking about what I'm now saying. I wasn't even thinking about that yet. So I only became strong with it.
Yeah, good.
So there's another question. Someone's asking, how do you represent intransitive verbs?
Oh, I mean, it's simpler, huh? So I think the question probably, if I may guess and speculate, is hinting, how do you go from a transitive verb in use to an intransitive counterpart? Now, an intransitive verb, like, I mean, what I'm talking about now, part of it is like how the computation, Lambek and Co have dealt with it. So a transitive verb has three types. So this would be the sentence, a noun and a noun. An intransitive verb is a bit smaller, produces the sentence when you give the noun. So you got like say Alice and you stick it in here. Now the question is, many verbs which are transitive can be used intransitive. It's kind of the same too for like adjectives which can be used as nouns. So an adjective would be something like this, and then so like drunk Bob is drunk Bob, and then you want to turn it into maybe the noun drunk, which is a different thing. You can, I mean, the naive first thing we do is we use these spider things to delete that. In fact, in many cases, what we would do here is we treat drunk as a noun, and then we use the spiders to turn it into two types. I mean, this is what in I mean, Martha told me that, Martha Lewis, like, this is what people in some contexts call intersective adjectives. So they're kind of acting like they're a noun themselves. Of course, they're acting upon something, but really the space in which they live is like a noun. And you're basically here, for example, this is the person who's drunk, and which is one property. This is the idea that you're drunk, which is another property. And then if you use your spider rules, you basically get this picture, which is really just like an intersection monoid taking those two properties together. And the same happens here, going from a transitive verb to an intransitive verb. That maybe you could take the intransitive as the default and then build the transitive, or the other way. I mean, this requires some research, and language is not a perfect science, so there is not a unique way to do this. And it's also quantum and natural language processing also about like making useful approximations and then building a little bit further on them. But fundamentally, this is the type, and you could just build it from this by just ignoring basically. So this you can think of this as summing over all possible objects. You sum, so this thing is actually a sum. So you can think of this as summing over all possible objects. So Bob drinks means he drinks something. It can be anything. So this is like a quantifier. This is like a quantifier.
Okay, thank you. There's some more questions. I encourage you people to ask the questions on Zulip rather than here in the chat, because in case they don't get answers, they'll stay there and they can be answered in the future or start a discussion. Anyway, maybe Konstantinos and Alexis, are there more unanswered questions?
There's a question on dynamic insignificance and like bring belief into the story, and I was gonna write an answer on dynamic epistemic logic and that kind of stuff, but so it was a comment on your meaning is use.
Right. I mean, is the question about the difference between like what an agent believes versus like true statements and stuff like that?
Yeah, I guess it was a question of how do you put this work in
the influence
context
on
where you have action and belief as well.
action, yes, especially in action as part of the notion of meaning or significance or influence.
So yeah, so I mean, obviously, like if you go to sort of vector space model of meaning, then all meanings are static; they never change. So Alice was the same at the time of the Big Bang as she will be at when the sun explodes and whatever. So and in first order, what we were doing here was, of course, working with static beliefs. Now, of course, the more natural thing is to go to dynamic beliefs, and within this formalism, the first time we consider this in a paper which is entitled "The Mathematics of Sentence Structure" from last year or something, which I wrote. And the idea then is that you don't treat agents as state anymore, because states are static things. I mean, as represented in triangles, you treat them as the wires, which then are actually evolving triangles. And then things like verbs, they tell you new things and they update the state. So you start to get much more the feeling of dynamic epistemic logic, where things get updated. So say, okay, I've got a car. Next sentence, okay, I've got a red car. Okay, it's a fast car, and so on. Or blah, buried, blah. And you start, so you use these things actually to update. And what you get is actually a circuit for them. So you could maybe, yeah, maybe this is good. Like think of this Alice, this is Bob. So you start with Alice, you start with Bob. This is like, you think of this gate as a sentence, and it says, oh, suddenly Alice and Bob are married. Okay, it goes on. They can divorce at a later stage, by the way. So they're not married anymore. And obviously, this doesn't mean they're disentangled, because they couldn't probably hate each other like hell. So this disco circ thing is really about a circuit in which things get updated. And this thing, and I remember at some point when I first started talking about it, like Alexis said, I'm not sure about that. And then when they start to implement things as circuits for the quantum computer, say, oh, I think we rediscovered disco circ. It actually works, something like that. So yes, and then you get these updates. Now, what are you updating? Are you updating reality? Are you updating the belief of a certain agent or the knowledge of a certain agent? I mean, this would be a layer on top. I would imagine that everybody has his own diagram, and then you can do, I can imagine some Baltak, Moss, Solecki style stuff where a diagram is your own, you got your own diagram, you got your diagram of the reality, you got somebody else's diagram. Of course, they are very closely connected and they interact with each other. That's the way I would think about it. I mean, I worked a long time ago with Baltak on this dynamic epistemic logic, so it's always in my mind. And I've got a student now specifically working on this sort of things, like solving puzzles. She's doing Fanny. She's doing a master thing specifically on trying to get dynamic epistemic logic ideas in this form, which I think is the question. But I mean, yeah, that's how I would do it. I would take away the sort of propositional descriptions by this, and then do the same sort of agency stuff as Baltak, Moss, Coecke are doing, something like that.
Thank you. By the way, everybody who's giving references to papers, works, and repos, please also do that in the Zulip channel, so it's going to stay there.
I guess I can just copy and paste the beginning of the conversation out there and start it.
So there's another question. Someone's asking, if I give you a non-intersective adjective like favorite, would that just be a state with two lines coming in?
Yes,
The
yes.
agent gets
Yes,
hooked up
yes,
to the person
yes.
needs to be hooked to.
Yes, I mean, obviously the structure of something like that is much richer, like, and even things like, I mean, it's not that an adjective is either intersective or not. It's also the context you put it in, how it behaves. Like red meat is a very different thing than red wine. I mean, it's different kind of reds. So there's no absolute red going on there. I mean, that makes things complicated, of course. So you have to go to a higher type, and from a state you go to a map. So 2 wires, indeed.
Okay, any more unanswered questions or any more new questions? I see Martha Lewis is also answering some of them.
Oh, that's good. Hello, Martha. I think some level of autism is good for this kind of talk. Or maybe some level of drunkenness, that's the same.
So there doesn't seem to be any more questions. Of course, you're always free to ask more of them in the future. The Zulip channel is going to stay open. So let's thank our speaker again. Thanks for the talk and for the.
So yeah. I mean,
setting.
Like another place, like even if later you come up with. I mean, it seems that a lot of the applied. I mean, I didn't know that. Amar told me that that there's lots of activity at Twitter. So a month ago, I joined Twitter, and you can find me there. And I know Alexis and Giovanni and Constantino, they're all there. So if you just like ask questions there, or for example, the announcement of the talk today, then you're going to get answers by all of us. If we forget to look at Zulip, for example. So that's a place where I think you can also keep on asking questions about all this stuff. And you also will see updates on how these things are moving further. Yeah, so I mean, given that so many ACT people seem to be moving there now, like, yeah, I mean, I said, okay. I mean, I'm always late with things. I loved it today to really go back to non-slide presentation, because I was very late to go for like computer slides and stuff. I love these sort of things more. But yeah. Okay, bye everybody. If that's the
Thank you so much.
time of ending.
All right. So I'm now going to end the stream. Whoever wants to stay, we're going to have breakout rooms in a minute. Of course, anybody else is free to leave, and in any case, always feel free to post on Zulip.